Welcome everyone to our solar photovoltaics course. Today we are having the 8th week and today is our 5th lecture, which is the final lecture. So, in this week we have been discussing about the different characterization systems or some of the common technology which we need to know in the context of the solar cell. We have discussed about the vacuum technology, which is very important. We have discussed about the imaging technology, and then the another thing which is very popularly used nowadays to measure the electrical parameters of the solar cell is the impedance spectroscopy. In today's lecture we will learn about impedance spectroscopy. Now, the resistance is the ability of a circuit element to resist the flow of electrical current. Now, we all know that what is a resistance is there. Now, Ohm's law defines resistance in terms of the ratio between the voltage E and current I. I know that usually you assign the voltage as a V, but let us consider the voltage V is as a letter E. So, the resistance according to the Ohm's law R is E by V, E by I, or which you know as V by I. So, instead of V I have written E. So, E by I. Okay. Now, while this is a well known relation, its use is limited only one circuit element, the ideal resistor. Now, let us say when we are talking about this Ohm's law about the resistance, so basically that corresponds to only the ideal resistor. But what happens if I have a capacitance? What happens if I have an inductance? Then obviously this E by I relation will not hold. An ideal resistor has several simplifying properties. It follows Ohm's law at all current and voltage levels. Its resistance value is independent of frequency. AC current and voltage signals through a resistor are in phase with each other. Now, obviously at all current and voltage level the Ohm's law is valid. But what will happen, let us consider your voltage is a complex quantity. What will happen, let us consider your current is a complex quantity. Have you ever thought about that? If you have a complex voltage and a complex current, then will the resistance will be a complex resistance? Yes. In that case you cannot call the resistance as a resistance, we call it as a impedance. But before doing that, let us look at what do we mean by the complex number. I am sure that all of us have some basic introduction to the complex algebra, and we know that a complex number can be represented as the sum of a real part and an imaginary part. So, this is the real part and this is the imaginary part. So, and we also have learnt, or probably some of us know that we can find out the magnitude of this complex number, which is called the mod of complex number, and it is represented by these two sign by putting the z between these two lines, and this is equal to the square root of a square plus b square. And then another quantity in terms of the complex number is the phase. So, basically we can say that the phase of the z, if we call it as a phi, which is the phase of the z, so that is tan inverse b by a. Now, whenever we define a complex number, these two quantities is very important, its absolute value or its magnitude or modulus and its phase. So, this magnitude z and the value of phase phi, that defines a location or coordinates in the complex plane. Now, when you are talking about the current as a complex number and when you are talking about the voltage as a complex number, then obviously the resistance also becomes a complex number. So, then we do not call it as a resistance, but we give a separate name called impedance. In real world, circuit element that exhibit much more complex behavior. So, have you seen a electrical circuit, a very sophisticated electrical circuit which is made only of the resistor? No. We have like different resistance, we have capacitance, we have inductance, we have ionic components, so many different things. So, this element forces us to abandon the simple concept of resistance. In its place we use impedance, which is a more general circuit parameter. Like resistance, impedance is a measure of the ability of the circuit to resist the flow of electrical current. So, the definition is same. Impedance, as the name suggests, it impedes something, it prohibits the flow of something, flow of what? Electrical current. Unlike resistance, impedance is not limited by the simplifying properties listed above. Electrochemical impedance is usually measured by applying a small AC potential to an electrochemical cell and measuring the current through the cell. So, when we talk about the electrochemical impedance, we apply a very small value of the AC potential and then we measure the corresponding AC current in the cell, and that gives us the electrochemical impedance. Suppose that we apply a sinusoidal potential excitation. The response to this potential is an AC circuit, AC current signal containing the excitation frequency and its harmonics. This current signal can be analyzed as a sum of sinusoidal functions, a Fourier series. Electrochemical impedance is normally measured using a small excitation signal. This is done so that the cell's response is pseudo-linear. Linearity is described in more detail in a next section. In a linear or pseudo-linear system, the current response to a sinusoidal potential will be sinusoid at the same frequency, but shifted in a phase. So, basically why we prefer a linear system, because a linear system or a pseudo-linear system, for that say, if we apply a sinusoidal voltage, so in the output we will also get a sinusoidal signal, only there will be a phase shift is there. It is not that I apply a sinusoidal signal and I am getting a triangular signal at the output. So, that is the linear signal. So, basically it restores the shape or the information of the signal. Okay. So, inductance or this impedance spectroscopy measures the impedance of a system to the applied voltage. So, as I said that it is a function of the frequency. Now, we are applying a voltage, the potential, which is a function of the frequency, E is a function of omega, and the current also become an AC current, which is a function of the frequency. It contains the excitation frequency as well as its harmonics. So, that is why the impedance is also a function of the omega. Since Z changes with the applied signal frequency, Z must be measured as a function of frequency and resistance of sample evaluated. So, let us say I have an unknown sample, I want to measure the impedance of that sample. So, since the impedance depends upon the frequency, so the impedance should be measured as a function of the frequency. So, I will do a frequency sweep and I will measure the corresponding impedance at each and every frequency. It is known as the AC impedance spectroscopy. This technique is known as the AC impedance spectroscopy or complex impedance spectroscopy, and also known as the electrochemical impedance spectroscopy when applied to electrochemical systems. Now, there is another important thing is here. Nowadays we can also do the impedance spectroscopy in the absence of the light or also in the presence of the light. Even in the presence of the light, we can modulate the intensity of the light, which is the intensity modulated impedance spectroscopy. Now, electrochemical impedance is normally measured using a small excitation signal. Now, as an excitation signal, we are giving Et is E0 exponential I omega t, where omega is the frequency of the signal and E0 is the basic amplitude. So, I plot E versus t here and you can see that this is a sinusoid. So, the corresponding current will be It is I0 exponential I omega t and there will be a phase shift. So, minus I phi. So, it contains the frequency of the excitation and there will be a phase shift. So, but still it is a sinusoid. So, the corresponding current will be a sinusoid, but there is a phase shift. You see that the trough and crest, if you look, they are displaced, like the top position is here, but here it is here. So, there is a phase shift happening here, right. So, what will be the impedance? By definition we know impedance is E by I. So, it will be, we can also write impedance as Z naught exponential I phi, that is amplitude and the phase part. So, that is basically the ratio of Et by It. So, basically it is E0 exponential I omega t divided by I0 exponential I omega t minus I phi, and Z0 exponential I phi you can write it as Z0 cosine phi plus I sin phi, because e to the power I phi we can write as cosine phi plus I sin phi. So, basically there is a real part is there and then there is an imaginary part is there. The conventional instrument system, here what we have, there is a system which is connected to a load cable to a potentiostat, where you can the potentiostat is used to apply the AC voltage here, and for the data requisitions we use a control signal which is connected to a computer along with an FRA, and block diagram here of the AIS measurement system of an electrochemical system. Okay. Now, once we get the data, so we represent the impedance data by two plot. One is called the Nyquist plot, another is called the Bode plot. Now, let us first see about the Nyquist plot. So, the Z is the ratio of E by I, which is Z0 exponential I phi. As we said that we can write it as Z0 cosine phi plus I sin phi. Z omega is composed of a real and an imaginary part. Real part is on the x axis. So, here we put the real part and imaginary part we put it on the y axis and the imaginary part on the y axis of the chart. So, if we put the real part along the x axis and the imaginary part along the y axis, or you can write it as z prime and here you can write it as z double prime, where z prime actually signifies the real part and z double prime signifies the imaginary part, then this graph of this real part versus imaginary part, that is called a Nyquist plot or also called Cole-Cole plot or Cole-Cole plot. Impedance is represented as a vector of length z. Obviously, like let us say I have a complex quantity z is equal to z naught cosine phi plus I z naught sin phi. You compare it with z is equal to a plus I b. So, this is the real part a and this is the imaginary part, right, b. So, now if I plot a diagram of the real and imaginary part, so I will get the location like this point which corresponds to z prime and z double prime. So, now if I connect it with the origin and so we will get a line like this. So, this is a vector. So, this vector actually represents the complex impedance and the magnitude of this vector will give you the magnitude of this impedance, and this vector whatever the angle it subtends to the x axis, that gives you the phase of this vector. So, that gives you the phase of the impedance. Okay. And now you see that the frequency that we are sweeping from a low frequency to a high frequency. So, towards the y axis we get a high frequency value, and as we go further and further away from the origin we get a low frequency value. So, impedance is represented as a vector of length mod z. Angle between this vector and the x axis is the phase angle, which is represented by phi. There is another representation of the impedance spectroscopy called Bode plot. So, in Bode plot the impedance is plotted as a function of the frequency, or the phase angle is also plotted as a function of the frequency, because in impedance spectroscopy basically we are changing the frequency. So, the impedance is plotted with log frequency on the x axis and both the absolute value of the impedance mod z, which is z naught, and phase shift on the y axis. So, either in the x axis we can put the log of omega, the frequency, and the y axis we can put log of mod z or z naught, which is the amplitude, or we can put the phase phi, which varies between 0 to 90 degree. So, this kind of the data where you plot the amplitude versus frequency or the phase versus frequency, that is called the Bode's plot or Bode plot. Now, this was the ideal case, but what will happen in a real system? The real system, there is a deviation from the ideal case, as is always. So, we get a distorted semicircles, and this distorted semicircle may arise due to the overlap of semicircles with various time constant. Now, this radius of this semicircle, that gives the time constant on the circuit. Depressed semicircle may arise due to the electrolyte is not homogeneous or distributed microscopic properties of the electrolyte. Slanted or curved spikes may arise due to the unevenness of electrode electrolyte interface or charge transfer across the electrode or electrolytes interface, diffusion of species in the electrolyte or electrode. This deviation is explained in terms of a new circuit parameter called constant phase parameter. So, there can be deviation from the real circuit, and that is called constant phase parameter, and constant phase parameter can be due to the different regions. Now, one important thing to mention here that, so by impedance spectroscopy we can analyze the circuit. So, when we have talked about the solar cell, you remember that we have discussed about the equivalent circuit. So, we said that any kind of solar cell can be represented by an equivalent circuit. Now, once we have an equivalent circuit, so we can use that equivalent circuit to model and feed the corresponding impedance. So, that means for any kind of solar cell, if we do an impedance spectroscopy data and if we consider an equivalent circuit for that, and if we feed that using that impedance equivalent circuit, so we can get the corresponding electrical parameters for that devices. So, by corresponding electrical parameters I mean the series resistance, the shunt resistance, the capacitance, double layer capacitance, or any ion diffusion or Warburg impedance. So, all of these different parameters which is actually the performance parameters of the solar cell that can be extracted just by analyzing the impedance data. So, that is why impedance spectroscopy is a very powerful tool in the photovoltaics. Now, let us talk about the circuit modeling for an ideal resistor and capacitor. You see that if I have an ideal resistor like this, which is a pure resistance. So, then the impedance spectroscopy data, if I plot Z prime versus Z double prime, so it is just a dot on the real x axis, okay, and this value of this is the value of the resistance. If it is 100 ohm, so that means this length is 100 ohm, and if you have a pure capacitance like this, which is a pure capacitance 100 microfarad capacitance for example, let us say, if I plot it in the Z prime versus Z double prime, so it will looks like a solid dotted solid graph. So, it is again a straight line along the y axis, but it represents by the solid circles. Now, what will happen if I put together both an R and C? So, I will have both this point which is shifted along the x axis and both this point. Okay, now, let me ask one question. So, obviously from this figure we can see that this R has a definite value. Now, if R is 0, then this will be at this point. So, when I am talking about the capacitance here, pure capacitance, so we consider R is equal to 0. Now, similarly, if we have a capacitance value of 0, then basically it is a simple dot. So, if I have both resistance and capacitance, then I have to come from the origin along this distance, and then also I have to go along the y axis to represent both R and the C. So, that is why in a real RC circuit, as you will see in the next slide, in this slide, a real resistance and capacitance combination, you can see a shift along the x axis and shift along the y axis, and that is very obvious. Let us say I like to plot something like 2x plus 3y. So, what I will do? I will plot along the x axis and I will also plot the y axis. I will go 2 unit along the x axis, then I will go the 3 unit along the y axis, and I will get this point which has a coordinate of 2 3 and which actually represent a vector 2x plus 3y. If I add a unit vector to this, I will get a vector. Now, similarly, the resistance and capacitance combination can be represented by a displacement along the x axis and the y axis. Now, the question is, a resistance and the capacitance can be combined in two different possible ways. It can be either in series or it can be in parallel. So, if the resistance and capacitance are connected in series, our previous example 100 ohm resistance, 100 microfarad capacitance, but now they are connected in series. So, what will be the corresponding impedance graph looks like? So, the resistance has been shifted along the x axis 100 ohm and then the capacitance along the y axis. This is for the series circuit. It can also be connected as a parallel. Here you see the resistance is connected in parallel to the capacitance. So, in this case what you will see that the impedance for the RC connected in the parallel, that will gives you like this kind of semicircular look, okay. And then this the diameter of this semicircle is R, or this part is R by 2, and here the value of the capacitance is shown here, and this value of omega is changes. At this point the value of omega is maximum, and that maximum value of the omega gives the time constant of the circuit, and that is 1 over RC. So, if it is a series resistance and capacitance, it is only a point and then going up as a straight line, and if you see a semicircle, that means resistance and capacitance are connected in a parallel, where the time constant is 1 over RC. Okay. Let us take an example. Okay. So, I have this kind of impedance graph, this is my x axis, this is my y axis, this is the z prime, this is the z double prime, right. So, what I have seen that I have a curve like this semicircle, it is does not start from here, but it has shifted and started from here. So, what does that mean? So, as we know that it intersects along the x axis, and the intersection point is actually a point of resistance. So, that means it has a finite resistance at here and it has a finite resistance at here, and also it has a time constant, it has a capacitance value, and the time constant is R1 C1. So, basically, so here this R1, this value of the R1, this resistance and the capacitance, they are connected in parallel. So, if the resistance and capacitance is connected in parallel, then you will get this kind of circuit. Now, in addition to that, you have a resistance which is connected in series, that is why this displacement along the x axis, that is why this displacement along the x axis. So, there is a displacement by the amount of Rs along the x axis, and then there is a parallel combination of the resistance and the capacitance. So, if we draw the equivalent circuit, it will be a resistance Rs which is connected in series with a resistance R1 and capacitance C1 which is connected in parallel with each other. So, by doing some simple analysis, you can starting from an impedance data, you can draw the corresponding equivalent circuit, or if the equivalent circuit is given, you can find out the corresponding impedance data. Some typical plots for some electrochemical system is shown here, like which you will see experimentally when you do the impedance spectroscopy for solar cell. You can see a semicircle, but we already know that what does it mean, right. So, this is Rs, this is Rs plus R1, and the time constant tau is R1 C1. So, basically this is a series resistance which is connected, or is a resistance which is connected in a series to a parallel resistance and capacitance, where the last resistance and capacitance they are connected in parallel with each other. It can be two semicircle, but the diameter of the semicircle is different, right. So, that means the value of the resistance is different. So, that means we have one resistance here, another resistance R1 here, another resistance R2 here, and the value of R1 and R2 is not same, and we have also two different capacitance C1 and C2. Okay. Now, you look here, there is a semicircle, in addition to that there is a spike is here. So, the semicircle means, so there is a resistance here and then there is a capacitance is there. So, if this semicircle touches along the x axis, I know that there is another resistance component R1 is there, but instead of touching, it is going up along the y axis. So, this part comes due to the ion diffusion, and that is called the Warburg diffusion. So, if you see a semicircle with this kind of spike, so then there are the resistance capacitance along with the ion diffusion or the Warburg diffusion component in the circuit. Now, the semicircle can be depressed like this. So, that means, so the y axis has been put under the stress here. So, this is depressed semicircle. It can have two depressed semicircles with different diameters. It can also have a depressed semicircle with a Warburg diffusion coefficients. So, these are the common typical impedance picture you will see while analyzing the data. Sometimes the impedance data can be very complex, and one needs to consider a various kind of circuit model to get a best fitting. Now, the electrochemical elements or what are the different contributions of the electrochemical cell when we measure the electrochemical impedance are the following. One is the electrolyte resistance. So, in an electrochemical cell we use electrolytes. So, electrolyte can also provide the resistance, and that is usually called an uncompensated resistance. So, that is represented by Rs or Ru. Then there can be double layer capacitance CDL. There can be Warburg impedance related to the diffusion which is represented by W, charge transfer resistance RCT, or constant phase element Q. So, these are the different components. So, whenever we model the circuit, we have to keep in mind all of these factors. We have to consider about the electrolyte resistance, we have to consider about the double layer capacitance, we have to consider about the Warburg impedance, we have to consider about the charge transfer resistance, also we have to consider about the constant phase element. Okay, so, what is electrolyte resistance? So, resistance of an ionic solution. So, as in for example, when we talked about the dye sensitized solar cell, we have seen that we have used iodine triiodide as a liquid electrolyte, right. So, this iodine triiodide liquid electrolytes that stays in an ionic form. So, the resistance provided by these ions, they are the ionic resistance. It depends upon the ion concentration, it depends what types of ions are there, is it a cation or it is an anions. It depends upon the temperature of the system, and it depends upon the geometry of the area in which current is carried. So, basically, a knowledge of Rs or Ru, the electrolyte resistance, can tell you about the ionic concentration, it can tell you about the types of ions, it can tell you the temperature, it can even tell you the geometry of the area in which current is carried. In a bounded area with area A and length L carrying a uniform current, the resistance is defined as R is equal to rho L by A, where L is the length, A is the area, and rho is the coefficient of resistance. Now, what is double layer capacitance? You look at this graph schematic of an electrical double layer and its electrode and electrolyte interface model. So, here I have an electrode, and you can see that this electrode behaves like an adsorption layer. So, there are positive charge which lies at the electrode, and just on the electrode there are negative charge is there, and negative charge are what? They are adsorbed ions. So, these negative charge are adsorbed ions, electrode is positively charged. So, there are positive charge here, and then there are adsorbed ions are here. Okay. But in addition to that, there are solvated ions are also there in the systems. So, this negative they are anions, okay, and this the gray circle they are the solvent molecules. Now, you see that the solvent anions they are been encircled with the solvent molecules. Now, what will happen over the time, the solvent molecules along with the solvent anions they can also come in the vicinity to this adsorbed ions. Okay. So, so this distance from the electrode to the layer of the one layer, this is the adsorption layer, and then there is a one more layer is there. So, that layer is called the Helmholtz layer. Beyond the Helmholtz layer we have the diffusion layer. In this area there is a free diffusion of the ion is happening, but at this area once you come to the dotted boundary, these electrons are attracted by the electrode here. So, these are not the ions which is adsorbed on the electrode surface, but they stays to the vicinity of the electrode, but they cannot go outside the electrode also. So, these two different kinds of ions or the two different layers of the ions can give rise to the two different capacitance, and that is called the double layer capacitance, and this distance is the Helmholtz layer. Beyond the Helmholtz layer you have a diffusion layer. So, ions from the solution stick on the electrode surface. So, ion from the solution can stick on the electrode surface, as you can see it here. Charges of this ions separate the charges in electrodes. So, since there is a charge is there in these ions, so they can separate the charges in the electrode. So, that is why they will pull only the positive charge close to them, and separation is very small or the order of angstroms. The third part in this case is the charge transfer resistance, RCT. Now, the electrode reaction is composed of charge transfer, adsorption or desorption or mass transport. Now, let us say I have an electrode which I dipped in an ionic solution. Now, what are the phenomena can happen? Ions can come and sit on the electrode, or if there are ions already seated on the electrode, they can go outside the electrode. So, that is called adsorption or desorptions, and then the electrode can transfer the charge to the ions, that is called the charge transfer, or there can be a mass transfer also. So, there are these three different phenomena can happen. We have already seen what is the adsorption and desorptions. Now, we will look about the charge transfer. Charge transfer may occur between the electroactive species and electrode. So, for example, if I take a platinum electrode and then if I dip that electrode in some kind of charged electrolyte solutions, so then there can be a charge transfer between the electrode and the electroactive species. If no electron transfer, RCT becomes very large. So, if there is no electron transfer between the electrode, if there is no physical electron transfer between the electrode and the electroactive solution, then the value of the RCT is very large. If there is an electron transfer reaction, RCT becomes smaller. So, for a electron transfer reaction, charge transfer resistance value will be smaller, and if there will be no charge transfer reaction, then the RCT value will be larger. It connects in parallel with the double layer capacitance C. So, the charge transfer resistance or RCT that is connected in the parallel with the CDL or double layer. So, whenever we have a electrode electrolyte interface, we will have a double layer capacitance and we will have some possibility of the charge transfer resistance. One more important thing is the Warburg impedance. Now, this Warburg impedance that is created because of the diffusion of ions. Now, the ion can diffuse inside the solvent in the system. So, because of the diffusion of the ion, this Warburg impedance, so the spike things comes. At high frequencies, the Warburg impedance is small. So, where is the get the high frequency? Towards the origin. There the Warburg diffusion component is small. At low frequency, the reactants have to diffuse further, thereby increasing the Warburg impedance. So, as we know that, see what is impedance? Impedance is the obstacle the electrons or ions will feel. Now, when the frequency is high, so that means the number of vibration per unit time is very high. So, then they will not feel that much impedance. So, that is why the value of the impedance is small. The ions, whatever it ions is a massive, let us say it is considered as a massive charged particles. But when the frequency is value is low and then it has to be diffused further, thereby the value of the Warburg impedance increase. So, the Warburg impedance is represented by this kind of spike or the straight line. Okay. Nyquist plot for a Warburg impedance. The last thing was in those electrochemical parameters constant phase element. In general the constant phase element, or if you take the first word CPE, that has the properties of the resistance and capacitance R and C. So, in general CP has the properties of R and C. Mathematically impedance of a CP is given by the complex quantity ZCP is 1 over y naught z omega to the power whole n, which is equal to z naught, which is the absolute magnitude or the modulus of the impedance, times j omega, which is a complex number j omega, the frequency, times minus n, where the values of n runs between 0 and 1. When n is equal to 0, z is the frequency independent and z naught is equal to r, and Cp is the pure resistance. But when n is equal to 1, z is equal to 1 over z omega y naught, and hence y naught is equal to C, Cp pure capacitance. So, the constant phase element can be either pure resistance or it can be pure capacitance. For the values of the n in this equation, like z is equal to 1 over y naught j omega to the power whole n, right. If you put n is equal to 0, so what will happen? This to the power 0, then there will be no frequency term, it is 1. So, basically what you will get, that z naught is nothing but r, that is the pure resistance, and if the n value is 1, then z will be 1 over y naught j omega. So, what is that? That is nothing but the capacitance I omega into y naught. So, that is a pure capacitance. So, for the other values of the 0, n and 1, for the values of the n between 0 and 1, there will be a mixture or combination of the resistance and capacitance. So, constant phase element OYCP, that is y naught omega to the power n cosine n pi by 2 plus j sine n pi by 2. Now, for n is equal to 1, capacitance C is equal to y0. For n is equal to 0, we have seen it is resistance R is equal to 1 over y naught, 1 over y naught is the resistance R. N is equal to half, it is Warburg. So, sigma is equal to y naught, and n is equal to minus 1, it is inductance, L is equal to 1 over y naught. So, non-ideal capacitance n less than 1 between 0.8 and 1. Now, what are some of the application of EIS? First of all, it has been commonly used in metallurgy for the study of corrosion of metals. It has been used for the study of adsorption and desorption to electrode surface in electrochemical spectroscopy. It is used in the study of electrochemical synthesis of materials. It has used for the study of the catalytic reaction kinetics, and also for the study the ion mobility in the energy storage device such as batteries and supercapacitors. And it has been extensively used to find out the ion mobility Warburg diffusion coefficient in perovskite solar cell and in organic solar cells also. So, the theory of the ion migration or the Warburg diffusion, that comes by the possibility or when this impedance spectroscopy was done on the perovskite solar cell. But there are some limitations also of this impedance spectroscopy. Many parameters do not fit, like sufficient amount of data you always need to fit the parameter, and since it is a fitting, it can always generate errors. So, depending upon like what is the equivalent circuit we are considering and how much the good is our fitting parameter, that will give the reliability of the data. Overlapping processes in the frequency plane may not be separated, and in theory an indefinite number of equivalent circuits can be used to explain a recorded spectrum. So, that means one can use n number of equivalent circuit, there can be so many possibility to explain a spectrum. So, then there is no like uniformity or ubiquitousness, somebody can explain it in this way, somebody can explain in another way. But in most of the cases, if we know the some common spectrum, and if we know about the photophysics of the systems, then we can correlate the photophysics with the impedance spectroscopy, or in other way the impedance spectroscopy will give you an excellent overview about the electrical parameters and the interplay of the ions and the electrons in the advanced solar cells like perovskite solar cell or perovskite silicon tandem solar cells. Now, this field is very vast. There are lot of emerging techniques which is now associated with the impedance spectroscopy, and it has been extensively used nowadays. You can look lot of references. For example, some of this is given here. One of them is impedance spectroscopy theory, experiment and application, and then there are electrochemical impedance spectroscopy in fuel cell, PEM fuel cells, fundamentals and applications, electrochemical impedance spectroscopy in PEM fuel cells, fundamentals and application by Springer, impedance spectroscopy application to electrochemical and dielectric phenomena by Wiley, and electrochemical impedance spectroscopy by Wiley and Sons. So, there are a lot of books are there, and it is also worthwhile to mention that there are a lot of excellent research papers are available in this area. So, if you are really looking for working in the impedance spectroscopy for solar cell characterization, then there are a lot of research paper is there which explains how this impedance parameters of a solar cell can be analyzed to correlate its photophysical properties. So far, like as far as the some advanced characterization system is concerned, we have discussed about some basics like vacuum technology, which is very essential if somebody is working in the photovoltaics field. We have discussed about some advanced imaging technique like scanning electron microscopy, which is also required to know optimize the morphology of the film, and then there is some advanced characterization techniques for the electrical parameters like static and dynamic parameters of a solar cell to optimize the efficiency of a solar cell, that is done by impedance spectroscopy, that has also been discussed. Now, there are several other advanced characterization techniques is there. For example, if I like to study the morphology of a solar cell, then in addition to the ACM, one can do atomic force microscopy also. Now, in atomic force microscopy, that comes in different combination, like it can be conductive atomic force microscopy, and then there are Kelvin probe microscopy is there. So, then there are like different varieties of this AFM technique is there. Then some people use the STM also. Similarly, if we talk about the photophysics, so not only the impedance spectroscopy, one can do a time result spectroscopy like TCSPC, time correlated single photon counting, where the time resolution is low. To circumvent that, there are like femtosecond time result spectroscopy. So, we can find out the transient absorption spectroscopy or photoluminescence spectroscopy by using femtosecond laser spectroscopy. So, all of these things will give you the information about the defect states, it will give you the information about the location of the defect states and various other information, what kind of charge transport is happening in the systems and what is the reason for the recombination in the system, where the recombination is happening, etc., etc. Similarly, like if somebody wants to know more about the mobility of the system, there are different methods is like that. For example, this SCLC method, space charge limited current method, the time of flight methods is there. Now, in addition to that, there are this solar cell parameter characterization unit. Like in solar cell, you measure the current and voltage and fill factor. So, you measure the JSC, VOC and fill factor. Now, the standard multimeter which we use for measuring the current and voltage is not enough if you want to measure some sophisticated solar cell. So, there is a very standard system is there, this is called solar simulator, which mimics the sunlight by using an AM1.5 filter along with some broadband xenon light source, and there we sweeps the voltage and we measure the currents, and the instrument can generate the data of the quality factors, that the fill factors value. From there we can calculate the efficiency, and that is a standard technique for measurement of the efficiency. Again, if we talk about the stability of the devices, so then there is another instrument called humidity chamber, where we allow the solar cell with a different humidity level, different like temperature level, which is an environmental chamber. We allow the experimented aging of the system, and we measure the aging of the system or the degradation or the stability of the systems. So, in addition to that, there are several other characterization units to the solar cell like pulsed laser based systems, pulsed PV based systems, and then like as you have said that this conducting force microscopy, IR microscopy is there. So, there are a lot of advanced characterization systems are there, but these are the some of the techniques which is essentially required if somebody wants to work in a solar cell. So, I guess we have learnt some concept and understanding about the some characterization systems which is required for the solar cell or photovoltaics technologies. So, with this we will conclude this course, and I believe that you have enjoyed our whole course. Thank you very much for your attention throughout the semester.